Hi and hello to everyone. In this video we are going to discuss about the signal to noise ratio, noise factor and noise temperature in a communication system. Welcome to the lecture. First we will see about the signal to noise ratio. It's very clear, it's nothing but the ratio between the signal power to the noise power. That is the signal to noise ratio is the ratio between the signal power to the noise ratio. It is represented by the PS, which is the signal power divided by the noise power. At the same point, the here meaning is either it can be at the receiver end or it can be both at the transmitter end. Okay, at the input or the output, right? Okay, so if you are measuring the signal to noise ratio, you should measure both the signal power and noise power at the input or both the signal power and noise power at the output, right? That's what I mentioned here at the same point. You can express the signal to noise ratio usually expressed in decibel. What is in decibel? You have to take 10 log base 10 to the ratio, in the ratio that is your PS by PN. Okay, right. Now we can represent this power either in terms of signal voltage or noise voltage, right? What is signal voltage? This is PS is the signal voltage, PS square by R. What is the noise voltage? Noise power, it is V square by R is the power, right? So Vn square by R. Okay, so signal square by R is the power of the signal. Vn square by R is the power of the noise. So this R will get cancelled. So it is signal square divided by the noise square. Okay, so it's a Vs by Vn whole square. Now we can substitute express this in decibel. So yes, signal to noise ratio in decibel 10 log. This square will come here, right? So it's 20 log Vs by Vn. So two ways we can express. Either we can express signal to noise ratio in 10 log power of the signal divided by the power of the noise, or you can express in 20 log voltage of the signal divided by the voltage of the noise. Okay, so if you are using power, use 10 log. If you are using the ratio of the voltage, use it in 20 log. Okay, and you can see that it is always good to have a high signal to noise ratio. What is the meaning? The signal should be larger than the noise. So numerator should be always greater than the noise. So signal to noise ratio is higher, is always preferable, right? Okay, some other measures are used, right? They are like signal plus noise divided by noise. So this is another measure. Instead of signal to noise ratio, we can say signal plus noise divided by noise. Okay, this is one measure. Another measure is this synod measure. What is this synod measure? Is signal plus noise plus distortion divided by noise plus distortion, right? This method is used in specifying the FM receiver specification. This measure is used, right? Okay, there are three measures. The most widely used measure is the signal to noise ratio in decibel. There are some other measures like signal to noise ratio, signal plus noise divided by noise, or else signal plus noise plus distortion divided by noise plus distortion. This is another measure, right? Okay, now we will see how to find out the signal to noise ratio of an amplifier. Okay, so this is an amplifier. The amplifier typically has the noise in it, right? These are the terminals, the input terminals of the amplifier, which is AB. Okay, so this is the signal source ES, this is the source resistance RS, this is the input resistance RI. Now our objective is to find out the equivalent Thevenin circuit for this part. Okay, this part of the circuit we are going to find the Thevenin. So what is the voltage across AB? If I have voltage, that means I have to remove the amplifier, find out the voltage across AB, right? So if I remove this RS and RI will be in series. If I remove this amplifier part, this RS and RI will be in series. So I can apply voltage divider rule, find out Vs. Okay, so the voltage across this terminal is Vs is equal to total voltage multiplied with the corresponding resistance Ri divided by total resistance Ri plus Rs. By using voltage divider rule, we found out the voltage Vs, which is across the terminal AB. Then we have to find the equivalent resistance or the Thevenin resistance, right? So remove the source voltage, right? To find the Thevenin resistance, what is the rule we follow? Remove the source resistance. This Rs and Ri are in parallel, right? So it is Rs Ri multiply Rs and Ri divided by Ri plus Rs. Okay, now this entire part of the circuit will be converted to this Thevenin equivalent, that is a voltage series in series with the resistance. Okay, now what I am doing is, now again I am converting this amplifier with the noise into a noiseless amplifier. That is, I am bringing out the noise part outside it. Okay, inside it there will be definitely a noise part, right? I am bringing it outside, so this becomes a noiseless amplifier. So this is the AB terminal is there. This side of the AB terminal I am bringing in the noise part. So this is the noise resistance, this is the noise voltage. 4k t naught b Rn. This is the noise voltage, a square root of, right? Okay. Now what about the signal power? Signal power is nothing but signal power is Vs, so Vs square. What is the noise power? To find out the noise power, we have to remove the signal source, right? So this Rn and Rt are in series. We are doing Vn square, so instead of Rn, I am putting Rn plus Rth. Okay, right. So what is the signal to noise ratio? Signal to noise ratio is the signal power is Vs square divided by Vn square. What is Vn square? We are just plugging. Okay, so this is the signal to noise ratio at the input of an amplifier. Okay. Next, there are some other measures called noise factor. What is noise factor? It is nothing but signal to noise ratio at the input divided by the signal to noise ratio at the output, right? So you think you are having an amplifier, right? You are having an amplifier. Okay, this is an amplifier, this is the input side, this is the output side. Okay, so if you are able to find the signal to noise ratio I, SNRI, that is the signal to noise ratio at the input. This is the signal to noise ratio at the output. This ratio is called noise factor F. Okay, so what is it? The input signal power divided by the input noise power gives the signal to noise ratio to the input. What is output signal to noise ratio? Output signal voltage, output signal power divided by the output noise power, PSO divided by PNO. Okay, the ratio between this, again I repeat, the signal to noise ratio at the input divided by the signal to noise ratio at the output, SNRI divided by SNRO. Okay, and always it's remember that the input signal to noise ratio is much greater than the output, because output, how we obtain the output? It is after passing through the amplifier we get the output. Definitely the amplifier will have its own noise. Okay, so definitely the denominator is much smaller than the numerator. Okay, that's what I said. Signal to noise ratio at the input is always greater than the signal to noise ratio at the output, because the noise gets added to the amplifier. Ideally speaking, if this is a noiseless amplifier, if your SNRI and SNRO are equal, ideally the F's noise factor will be 1. Okay, now we will express this in the terms of power gain, right? What is power gain? Power gain is very simple. Output power divided output signal power divided by the input signal power. Okay, right? That is the G. This is given as the power gain. Now I am representing F. What is F? We know that PSI by PNI divided by PS0 by PN0. So I can rewrite it like this: PSI by PNI multiplied with PN0 by PSO. Okay, so we know what is G. What is G? G is output power, output signal power divided by the input signal power, right? So what is this term? Yeah, this term is your 1 by G. PSI by PSO. PSI by PSO is 1 by G. Okay, so PN0 PNI multiplied with 1 by G. Okay, so I am expressing F in terms of G. That is the power gain. Now our important factor is the output noise power. What is output noise power? PN0, I bring other terms to the left side. So PN0 is equal to FG PNI. And we know what is PNI, input power, input noise power is KT not B. Okay, so this is the, we are expressing the output noise power, okay, noise output power in terms of F noise factor, G power gain, and the PNI input noise power. Okay. Next, there is another term called noise figure. What is the difference between the noise figure and noise factor? It's very simple. If you take decibel to the noise factor, we will get noise figure, right? So noise factor expressed in decibel is the noise figure. Okay, so you take for the noise factor, you express in 10 log noise factor, you will get noise figure. Okay, so if you logarithm the SNI signal to noise ratio of the input divided by the signal to noise ratio of the output, the division becomes subtraction. Okay, so this is the noise figure. Then something called noise temperature. What is noise temperature? Right, here we are going to express the noise in terms of equivalent noise temperature. Okay, like we are going to represent this using a resistor which is dependent on the noise temperature, and it is used in ultra high frequency, microwave, low noise antennas, receivers, or other devices. Okay, this is the definition of noise temperature. Okay, equivalent noise temperature of a system is defined as the temperature at which the noisy resistor has to be maintained, so that by connecting this resistor to the input of a noiseless version, Okay, so assume you have an amplifier. You have an amplifier, right? Okay, this I say this is a noisy amplifier. Okay, so and here I have a noiseless amplifier, right? Noiseless amplifier, and here I will be connecting the noise resistance, right? I will be connecting the noise resistance, which is, okay, this is the noise resistance, I can say, right? Then these two are equivalent. These two are equivalent. That's what they say here. Connecting a noisy resistor. Okay, this noisy resistor, I am connecting a noisy resistor and I have to maintain it at a temperature, at a equivalent temperature, at a equivalent temperature. If I maintain, right, then what happens? The noisy resistor has to be maintained at a equivalent temperature, so that connecting this resistor to the input of the noiseless version of the system, it will produce the same amount of noise power at the system output as that produced by the actual system. Okay, if you are connecting this resistance, maintaining at an equivalent temperature, then this together will produce the same effect as the noise, produce the same amount of noise power at the system output as produced by the actual system. Okay, this is the definition of noise temperature. Okay, right. I hope you learned something useful from this lecture. Any doubts, you please ask in the comment section. Thanks for listening.